You ever want to talk about your emotions, Cian?
Well, hello. We have one person. Is this everyone? Yeah, so far. I've been sitting in here 10 minutes alone, so. I suppose let's just get going because I have all this material to present and at least one person to present it to. And if we don't get started, we're not going to hit the 4:30 p.m. leaving time. So, yeah. But hello. Let me share my screen. I gotta actually, hold on. Let me make sure I have the screen all set up on the right side. I need this here. Yeah, I think that's it. Doing this one. Okie dokie. So let's get this in presentation mode. Welcome, my one attendant, Sir Quincy Johnson, I think. We have the, yep, nailed that one. To the Introduction to SystemVerilog Part 1 workshop. So this is an IEEE official workshop. I don't know if that means anything. I don't think we have like a pledging event or anything. But yeah, the goal today, just to keep it in the back of our mind, is that we're going to be creating just a basic like digital logic vending machine. So the English description of it is it's a vending machine that takes in nickels and dimes. And then upon receiving 15 or more cents of any combination, it will dispense something. So that'll be our output. And it doesn't dispense out any change or anything complicated at all. It's basically just the simplest design of a vending machine we can go for. And so, like I said, it had the inputs, nickel and dime, and then also a reset input just so that we can get back to the beginning state at any point. And then one output, which is just the signal that would control like opening up the latch or however it works in an actual vending machine. So in order to create this vending machine in Verilog, let me actually open, I guess I can have the chat open in my other window. I don't know if that's going to help at all. That didn't work. There we go. Okay. So to create this vending machine in SystemVerilog, we're going to have to learn a little bit, and that is the entire goal today. Learn SystemVerilog by making something. So just a little introduction into what SystemVerilog is. It is a combination of a hardware description language and then the ability to simulate that hardware. So it's actually like literally a combination of languages. SystemVerilog, it takes over Verilog. So Verilog's no longer a language. It's been completely replaced by SystemVerilog. So Verilog is the actual hardware description language component. And then SystemVerilog added the capability of simulating and testing and verifying the hardware that you create in your Verilog code. The most common uses for it are hardware verification. So if you're working on like prototypes of like a PCB or something, you would create whatever your circuit's doing in SystemVerilog, and then via SystemVerilog's ability to simulate, you would verify that it's doing exactly what you want. And then the other most common use is FPGA programming. So if you don't know, FPGA stands for Field Programmable Gate Array. And it's basically just a collection of digital logic so that you can program it to have whatever kind of digital logic you want to actually execute. So in practice, it's basically like a dynamic circuit. So that's the most common uses for SystemVerilog and actually what it is. So let's go ahead and get into actually like, using SystemVerilog. So the first thing that we're going to need to do in SystemVerilog is creating a module. So a module is very similar if you're familiar with any other programming language like a class. And you can also think of it in terms of a physical like hardware. Like I have one little section of my PCB that's the adder circuit, and that would be represented by a module in SystemVerilog. So let's go ahead and get started on that. Really quick, by the way, since you're the only one here, Quincy, did you install System or Quartus Prime, the directions on the Facebook page? Feel free to unmute or talk in chat. I have Vivado for EC, but you guys have to do Vivado. Oh yeah, I remember Vivado. I always had to do it in a lab though. Yeah, very similar. I think Vivado is almost exactly the same. It might use Verilog or maybe VHDL. I don't remember, but I'm going to be doing everything in Quartus Prime, which is just, I think, Intel's version of a SystemVerilog IDE that also has like the ability to simulate and stuff. Honestly, I can't say that I would recommend it. It's a pretty clunky software, but it is what I learned on from EC 111, so that's what we're using today. So in Quartus Prime, the first thing we're going to want to go ahead and do is start a new project. It's got a nice new project wizard here. And so I just wanted to mention all the different steps we're going to have to use to go through this. So the first step is we're going to have to select a folder where we're going to be saving everything. So I'm just going to make a new folder and we will call it I think I already have a SystemVerilog workshop live. That's my folder that I did the brainstorming in. So you just have to find whatever folder you're going to want to save into, and then give your project a name. So today we're working on a vending machine. So let's just call it vending machine. And then one important thing is that in SystemVerilog, there's the idea of a top level design entity. It's like the top level module you're going to be working on. In our case today, it's going to be pretty simple because we're just doing one module. So the top level is just that one module. But if you do more advanced SystemVerilog things, you'll have like reusable modules you might want to add into different modules to combine all together and do one bigger thing. But so the emphasis on that is that whatever your top level design entity has to be the name, same name as the name of your project. So for us, it'll be really easy for vending machine, but it's just one stipulation you have to do. And then next we have this menu where we're creating this project from. So we can either do an empty project or a project template. I don't think I've ever used project template, and I don't even know when you would use it. So pretty much just select empty project on that one. And then here is where you are able to add in files. So for example, if you're working in class and you're given some base files, or if you've written previous modules you want to use, reuse in this project, this is where you would add the actual files for SystemVerilog. For us, we're starting just completely empty today, so we don't have to add anything. And then this is the most complicated page. So this is where you actually select, because remember this software is used to program, for the most part, FPGAs is where all the physical testing would be going on. So this is where you would select what FPGA board you're using. For us today, we're just learning the language and simulating it and stuff. So it doesn't really matter what FPGA we're using. So we could just select the first, but if you were actually using one, you'd have to find your correct model. The reason for that is because different FPGAs have different like hardware and setup and stuff that the Quartus has to know how to program it. But for us, again, it doesn't really matter today. And then finally, this is the last page. This is where we select what we're going to be programming in. So if you followed the directions on the Facebook, but you used Vivado, so you didn't. But the directions I linked, we start with model sim Altera is the simulation software we're going to be using that's going to allow us to see how our circuit's reacting. And we're going to be coding the simulation in SystemVerilog as opposed to VHDL. So that is all the pages. Then you get a nice little review of everything you've done, and you can go ahead and give it a look over. It's not super vital to us today because we're calling me out on the recording wall. True. Yeah, well, I guess that's the one downside of you being the only one to show up, huh? But thank you for showing up, Sir Quincy Johnson. Anyways, so yeah, we don't really have anything complicated going on in this page, so we can just go ahead and finish. And we're going to open up our project here. Oh, we have a third person. It's Tim.
That was good.
Yo, what's up, Tim? So now that we've made our project, oddly enough, it doesn't actually make the top level file for you. So you actually have to go make a new file. So file new, and then we're going to be making a SystemVerilog hardware description language file. Because that's what we're learning today, right? And I think it's very odd that they don't make one for you, because as soon as you make one and then go to save it into your folder, it'll give it the automatic name as the top level module, but it just doesn't do it for you for whatever reason. But since this is our top level module, remember this name has to match the name of our project. And since it autofilled, we're good to go. Okay, so now we have a module created. And then inside this module, there's a little syntax to creating a module in SystemVerilog. And it's not very complicated. It's very similar to creating a class in any other programming language, since these are almost analogous. So the first thing you have to do is create a module, and then whatever you want to call it. So I believe this name has to match the name of the file that you're working in. So you have to separate your modules to your different files. So since we're working in vending_machine, our module will be called vending_machine. And then we're going to have an input list and an output list here, surround like in parentheses, and then we'll have a semicolon after that. It will yell at you if you don't put the semicolon. And then finally, everything in between that module declaration and the line we're putting here, which is end module, and then you have to name the module you're ending. So everything in between these separators will be included in the module. And then the one part of syntax for SystemVerilog is you have to declare your inputs and your outputs for your module. So since we're working with our vending machine, we covered the inputs earlier. So we'll have input N, input D, input reset, and then we'll also have a clock. I didn't mention that. It was kind of just assumed that we're going to be working with a sequential circuit because we're doing a state diagram, but it will need a clock to run. And then, so that's all our inputs. Oh, you know what? This would not compile because I messed up. You actually have to specify the type of input. So we haven't covered types yet, but the most general one we're going to cover and repeatedly use today is the idea of logic, and we'll get to what that does in a second. And then we have to do our outputs as well. So our output, we'll again call it just a type logic, and we'll name it out like we have on the diagram. So this, we have our file set up, we have our folder set up, and we've actually created the module. All we have left to do now is make the logic for our vending machine in here. But that is the process for creating a module. We have another person joining us. It's Angela. I'm calling everybody out on the recording if it makes you feel any better. All right, where was I? Back into here. Okay, so that's the whole process. It's kind of long for creating a module because you have to specify so many things, but we're done there. So now let's go ahead and get into, or well, I guess we could stop really quick. So any of that, you have any questions, anybody on? It was basically step by step. It'll change based on your projects if you need to change anything, but for us today, that was step by step. Any questions on it? Okie dokie. If you have a question, feel free to put it in chat if you didn't get it out in time. So let's go ahead and actually get into learning the basics of SystemVerilog so that eventually we can program our stuff today. So the first part that I just mentioned and we didn't cover before making the module, but we needed in the module, is the idea of variable types. So there's, honestly, the variable types in SystemVerilog are pretty complicated. There's a lot of different types, and some of them can only be used in certain scenarios, either as like inputs or outputs or only in certain blocks or whatnot. We're only going to be covering the basic and most common ones today. And so the most basic type or the most, I guess, intuitively basic type in SystemVerilog is the idea of a wire. And its name is very accurate. It literally represents basically what a physical wire would do, in that it can connect different things. Say you're working with logic gates or modules you've created, you can connect them together using wires to inputs and outputs. But those wires can't actually store any values. That's their key thing. Another type we'll be working with today is the idea of a reg. It's short for register. And if you're familiar with registers from digital logic at all, it's pretty much exactly what these are. But they store values. So where wires can't store values, registers can store values. And those stored values will only change usually based on a clock. So that's going to be one of the most basic types we'll use. Anytime we have to store anything, it will be type register. And then the most common one you're going to see me use today is logic. So logic is kind of a default type that can pretty much be any other type in SystemVerilog that the compiler will automatically like change to what it needs to be for you. So anytime you don't know for certain whether it's going to be a wire or a register or any other type, you can just make a logic and then the compiler will be like, all right, well, this needs to be this type to work. So pretty much always the only word I type is logic and I let the compiler figure it out. It just makes it easier. And then finally, the last type we'll be using is the idea of a parameter. And so parameters are used as constants, just like any other language. It's just something you declare that you don't want the value changing at all, but you want to reuse it basically. And one interesting thing about parameters that we're not actually going to use today, but I figured I should mention, is they can be changed during the instantiation of a module. So when we're programming the module, we'll set the parameter and it'll be a constant value. But then when we wanted to use that module at other times, we can actually change the parameters in that module when we're instantiating it, which means, for example, if we do really good programming, then we could make a 2-bit adder where the amount of bits is actually specified by a parameter. And then if we wanted to reuse that code as opposed to being a 2-bit adder to say maybe a 4-bit adder, we can change that in instantiation and it'll work as a 4-bit adder. So let's go over to SystemVerilog and just see really quick how you would use these. So wire is super simple. You would just, it's similar to types from any other programming language. So you start with the name of the type. So it'll be a wire, and then you'll name the instance of that. So say we want input 1, for example, and that would create a wire with input 1. And we're not really doing anything with it yet, but it does exist. The other one, or the next one we had was reg. So registers, if very similar to physical registers, they have an amount of bits they can hold. So the typical way you'll see it in SystemVerilog is that you'll declare how many bits it is immediately after the type here. So for example, if we're doing a 4-bit register, the most common way to do it is you'll have your most significant bit first. So if we're doing 4 bits, we're going to be doing 4 bits, but 0 indexed. So our most significant bit would really be 3. And our least significant bit would be 0. So to specify how long they are, you specify your most significant bit -1 down to the index 0. And you have to do a semicolon in between because it just specifies basically from 3 to 0. So once we actually create a reg of 30, we can name it, say we'll do it output 1, right? To address into that, you would do output 1 and then whatever bit you want to access. So for example, 0 would give us the least significant. And then output 3 would give us the most significant. And it has to be within our index. So if you did 4, it would give you an error and be like, oh, there is not 4 bits in this and you can't access it. I don't believe there's any cool like indexing, like how Python, you can do like negative indexes and go to the back or anything. It's a pretty simple language, so it doesn't have that. And then the last one I wanted to mention is logic. We'll go over parameter too, I guess, but it's basically just the idea of creating a constant. But logic, you can do it at just in front of anything, and the compiler will let you or like figure it out for you. So for example, if I wanted to create a wire, but I didn't know, I'm just going to call it logic, and then I want it eventually on the way I'm using it's going to be a wire. I could just do logic, and then it'll be like output 1. Or I guess let's do fake wire. That'll be a good name. And you can also specify the length of logic. So if I want a logic, I don't know what kind of variable it's going to need to be, but I know it needs 5 bits. I can do it like that and then name it however I want. And the compiler will just take care of it for us. And then the final one that is the idea of a parameter. Parameters, you can specify size. You don't have to specify size because these aren't really synthesized. All of these other types will actually be synthesized into like hardware, whether it's a wire or a register or whatever logic works out to be, which may or may not be synthesized actually. Parameter does not ever get synthesized though. It's basically just a constant that we're going to use. So say we want to represent our state value as like 1 so that we don't, we could just reference instead of typing 1 and being like, why am I using a 1 here? We can instead be like, all right, I'm using a constant state value, and it makes it more readable. So are there any questions on any of those different types and when, where, and why you would want to use them? Feel free to unmute or ask in chat. Okay. So I'm just going to go ahead and delete this. This is just kind of like practice. I don't really want any of those yet, but we'll get to what we want eventually at the very end. So next topic we're going to cover. Oh, by the way, these, I mentioned a little bit at the beginning that these types are kind of odd in SystemVerilog and they have different places you can use them. I believe wire can be used pretty much anywhere. Register has to be used with specific blocks, and logic and parameter can be used anywhere as well, as far as I'm aware. If you're ever confused, you can definitely just look up the SystemVerilog, like when and where and what I can use. Would you mind muting whoever just joined? We have a bit of background noise.
Next. Ready for the next one?
All right. I think I can actually go ahead and mute people. Hold on, let me check that. Oh, I'm the best. All right. All right, next topic we have, we're going to be covering is if and else if statements. So these, if you're familiar with programming at all, honestly seem like the foundation of everything because this is how you control your logic, right? So in SystemVerilog, very, very similar to any other languages, if and else if and all of that. The syntax will be if, and then you'll have a condition. And so what's inside the if block between the begin and end that immediately follows will be executed if that condition is true. So since we're working in SystemVerilog, that equates to a value 1 because we're not doing anything but digital values. Oh, by the way, if you're not, I had a question in chat. What if I'm not familiar with programming? This would not be the greatest language to start with. I would start with something much similar to build up your programming before coming to this. Because it's kind of a weird language and it's very specific. Programming fundamentals wouldn't be great to learn in this language. So unfortunately, if you don't know programming very well, I'm sorry, not a lot of this will make sense, but if you have a basic understanding of pretty much any other language, it's pretty easy to build off of from here. Look into x86. All right, well, that doesn't sound like a good programming language to start off with either. All right, where was I? Right, the initial condition, or the condition inside your if, it'll execute if it's true, so which equates to a 1 when we're working with bits and digital stuff. And if it's not true, it won't execute that block. And I mentioned it briefly, but similar to any other programming language, which you denote like what you want to execute after the if with like curly brackets or indentation, for example, in Python. In SystemVerilog, it's anything between the begin and the end that immediately follow the if statement. It's pretty clear over here, and it's actually pretty nice. And you could do the tabbing as well, but the begin and ends are pretty nice to see, like your hierarchy going on in your code. So that's pretty good. I'm probably not going to show us a programming example of if and like this, because I think just looking at this setup over here should be pretty clear. So then the next concepts we're going to need to learn today to do our state machine and our vending machine is the idea of a switch case. And so a switch case, if you've seen it in any other programming language, it's very similar in SystemVerilog. So the syntax, it starts with a case, and then you input the variable that you're going to be comparing. So oftentimes in SystemVerilog, since we're working with digital logic, it will be things like a state variable that represents what state you're starting in. And then you'll have any number of states or cases that you want to check based on their values. And then inside those cases, you'll have the code that you want to execute if that condition is true. And they're also in Verilog, you will want to include a default case at the very end in case none of the conditions match, or else things will get pretty wonky. And I think it'll give you like a bunch of latches or something, which are not great. So let's go ahead and look at what the syntax looks like in SystemVerilog. So it's case, and then whatever variable you're trying to compare. So say we're comparing a state variable. And then the syntax is a little weird on this one because, you know, something like if you'd have a begin here, or sometimes you'll have like a semicolon. There's nothing that comes after the case. It's literally just case state, and then you'll have an end case. And then everything in between in here will be treated as a case statement. And so the syntax for the conditions you're going to want to check with this case is the value you're going to check. So say my state variable, if its value is 0, I want it to do something. So you'll do my value 0 and then semicolon begin. And anything between this begin and end will be executed if that state variable is 0. So say we want to make, I don't know, we'll do output equals 0. And then you can add as many cases as you want. So say we had a case for 1, same syntax, it's going to be 1 semicolon begin and end, and then whatever you want it to be. So say we have output equal to 1. So you would do this for however many cases you want, all the different logic. So when we're looking at our vending machine, I believe we had 4 states. So we'll likely have 4 state conditions here. And then we'll have one more at the end, which is the default, which will be run if nothing else is true. And so this one, you would just do whatever you want the behavior to be like if you missed all the other cases. So this would, you probably don't ever want to hit default So you probably want to set it back to like some good initial conditions, like out equals 0, and maybe change your state to the beginning one if it ever got here. But you do want to include it, or else if you don't have that default case, the way the hardware will synthesize, it'll have like a latch for certain values that it'll be hard to debug because latches don't actually like behave how we think they would when we're looking at our code. So that's why you want to add a default and make sure you don't have any of those. But that's the syntax for a case. Is there any questions on, I guess I should probably stay on the code. Any questions on what a switch case is, any of the syntax, or how or when or why we'd use it? Again, feel free to unmute or type in chat or anything. Okay, doesn't seem like it. And so then I think we have two more things to cover before we actually get to programming our vending machine. And so this one is one of the most important. It's the idea of an always block. So an always block is used to execute code according to different conditions. So for example, if we're working with our vending machine, which is going to be a sequential circuit, and therefore it has a clock, we probably will only want to execute things according to that clock. That's the whole point, it's there, right? So the SystemVerilog way to execute things according to a clock explicitly is the always_ff block. And what that will do is it will take in, so after every always block, there will be an @ and then a list of your conditions. So for the always ff block, it's specifically used to execute things according to a clock. So oftentimes the only sensitivity you'll see in that is the positive edge, which means it will only execute on the edge of the signal where it rises from 0 to 1. And then it'll execute all the code in the block when that happens. You can also specify if you didn't, for example, have pause edge here and you just had clock, that would execute anytime the clock variable changes. And you can also specify if you want the negative edge of an input just by, instead of pause edge, you do neg edge. So always ff, it's used explicitly to make the program more readable and know that whatever's in that always block is going to be clocked and have flip-flops to it. That's what the FF stands for. Another kind of always block we'll see is the always_cone, or it's short for always_combinational. And what it does is any variables inside its block, if they change, any one of them inside the block change at all, no matter the value, it will run all the code again. And what it's used for is simulating combinational circuits where anytime an input changes, you want your output to change as well. That's the idea of combinational. So that's what it's named and what it would be used for. In general, you can just do an always block. Let's go back to code. So we have our always_ff and usually it's the pause edge of the block. And then just like with our if and else if statements and stuff, you denote what's in this block between a begin and an end, and anything in here would get executed. And then there's, of course, always_com, which we just went over. So always_com doesn't actually take in any sensitivities like always_ff does. And the idea is because it will execute if any of the variables inside its block change. So you don't have to be sensitive to any particular thing. As long as it's in the block, it'll execute. And then the final one, this is just the generic one. It's the always @. So always_ff and always_com could be used. They could be made with just a simple always block. But we specifically use them as programmers to make it clear what our code's doing. So if anybody reads it, they'll be like always_ff. Oh, I know there's a clock signal that's going to be doing something here. So it's more explicit that way, but you technically could do it with this always block. But in general, the always block, just like our always_ff or any other always block, takes in a sensitivity list and executes when those sensitivities become true. So whether they're changing or a pause edge or anything. So if you just want to execute code according to maybe an enable signal, anytime it changes, you would do it like this, as opposed to doing always_ff, which would imply a clock, or always_com, which would possibly execute when you don't want it to do. So those are in general the three different always blocks. And like I was mentioning, these will any code between the begin and the end will be run anytime the sensitivity is true. So in the case of an always underscore FF, every single clock cycle will run the code in here. Does that make sense? What the always blocks are, kind of the syntax for them, and when you would use them? Again, if there's any questions, feel free to unmute or talk in chat. Okie dokie, doesn't sound like it. All right, and so now the last thing we're going to be covering in SystemVerilog before we're getting into our programming is finite state machines. And specifically, just because so much of our digital logic is based on finite state machines, and we draw up all our diagrams and everything like that. This is a super useful skill. Once you know how to make a finite state machine in SystemVerilog, you can do so many different kind of circuits. In fact, I'm not positive on this. I'm no professor or anything, but pretty sure you can represent anything as a finite state machine. Maybe not anything. There's probably infinite state machines, right? But let's go ahead and look at them in SystemVerilog. So the first thing I want to cover is this first block up here, the parameter and then the state variables. And so this is just kind of to help our programming, or at least the first part, these parameters. This is just to help our programming and code look a little cleaner. So instead of, we'll have definitely, in order to have a finite state machine, we'll have variables that represent our states, right? And so the different values of those different variables will represent the different states and what we're going to do with them. And so we could represent those values of the states as like actual binary numbers and be like, yes, if present state is equal to 0, 1, 0, 0, we'll do this. But that's not very clear. As a programmer, I have no idea what 0, 1, 0, 0 is supposed to represent. So in order to help us with that in SystemVerilog, we can create, like I mentioned, one of the data types as a parameter, which is just a constant at runtime. And we can give it a convenient name as a programmer while still representing the value we want. So for example, in SystemVerilog, let's go ahead and get rid of this stuff because that was just example code. So in our vending machine we're going to be working with today, we had four states. So we had, I know we're going to need 4 different constants for them. The first one will be sense 0. And then I'm just going to copy and paste this line down below. So we have sense 0, sense 5, sense 10, and sense 15. So we can represent, we just need 4 different values to represent these different states. So we're going to go ahead and just do the system of encoding states known as one-hot encoding, which means however many states we have, we're going to have that many number of bits to represent our states. And then one-hot encoding, where it comes from is that the value for our state is n bits, and then only one of those bits is going to be high for each state. So for example, sense 0, we will make it I didn't cover the syntax in the slides, by the way, but to specify a number specifically, like in a, what would that be, a specific format that you want it in SystemVerilog, you put the amount of bits you want that number to be, followed by an apostrophe, and then what kind of number you want. So for example, if I'm working with binary, it'll be apostrophe B. If you're working in hex, it'll be apostrophe H, and decimal will be apostrophe D. But we're going to be working in binary. So it'll be a 4-bit binary number, and we'll make this first state, remember, only one of these bits will be high. We'll make it the 4th bit is high. And so that way, instead of saying, checking the condition, is this number equal to 0001 when we want to check for the sense 0 state, we'll just check if it's equal to sense 0. And then it'll make much more sense in our programming, and it'll be more readable. And so let's just go ahead and do that again. All these different variables. So we're just changing which bit is high for each one. And oops. And finally, we'll have 4-bit 10. And then the other part I want to talk about in this section was obviously we'll need variables to represent our states. So since we're going with our states encoded as one-hot encoding, that means our state variables will need to be that many bits long. So we have 4 states, we'll need 4-bit state variable. So this is, we need to make a 4-bit variable in SystemVerilog. So I don't know what kind it's going to be. I just know logic will figure it out for me. But I know that logic needs to be 4 bits long, so 3 to 0. And then we need two variables. We'll need a present state and a next state. And that just comes from anytime we have, anytime we're in a state and we're checking conditions, we'll need to calculate what our next state comes from. And this comes from basically the digital logic, if anybody remembers ECE 25. So this will suffice to represent all of our different states. And then these are just to help us as programmers know which state's what. It's not explicitly necessary. You could literally just do binary numbers and check if it's equal to that value, but it doesn't look as nice. So the next part of a finite state machine in Quartus Prime is the actual state transition. So in the idea of digital logic and state machines, when you're in a state and certain conditions come in, you move on to the next state. And it happens in sequential logic every clock cycle, right? We check every clock cycle, what state am I in? What are the inputs? Where should I go now? So as it turns out, the logic for that in SystemVerilog is super simple. So we have the always block we always covered, or we already covered, always underscore FF. Because we're working with a sequential device, we're going to be working along a clock pulse. So that's why we're using always underscore FF. And then in our state diagram we had way back at the beginning, let's actually go back to it. We had every state, if we have a reset signal come in, we want to go back to our original state. So all of these will reset. And then depending on what state we're in, inputs of nickels or dimes will tell us which state we're going to go to. But going back to here, the logic for driving the state transitions, though, is very, very simple. The logic for determining what state I'm in, what inputs are true, and then what state I should go to is usually the complicated part. But the actual logic for I just want to change states every single clock cycle is really easy. It's like 4 lines in that always block. So let's go ahead and program it over here. So the idea is we're going to use the always FF block because we're going to be at every clock pulse checking our state, at every pause edge of our clock. And so in here, since we're checking the reset condition every time, so if our reset condition is high, i.e. something sent in a reset signal and we know we want to go back to our original state, we check that at every clock cycle. So if it is high, we want our present state to go back to our initial state. So sense underscore 0 is our starting state. So this, by the way, we haven't covered this yet. I've been using equal signs before, and I guess we could do it now. But in SystemVerilog, there are 2 different kinds of assigns you can do to a variable. So this just an equal sign is called a blocking assignment. And that means that any lines after that line will not get executed until this variable gets assigned. So for example, I did present state gets sense or equals sense 0, and then I did present state equals sense underscore 5, for example. I don't know why you would do this, but you could. First, it would get sense 0, and then it would get sense 5. And so the final value at the end would be sense 5. There's also another kind of assignment called non-blocking. And what non-blocking does is at the initial, once your code starts to execute, every non-blocking assignment gets determined. So it will calculate the right-hand side. So in this case, it's just a constant. So there's not really any calculation. And then once all of the non-blocking assignments, right-hand sides have been calculated, they'll all get assigned at the same time. So if I were to do this, the compiler actually would probably yell at me because I'm trying to assign 2 values to one variable, and it wouldn't know which one I really want to do. So we'll just go back with blocking assignments today, just because they make more sense. But yeah, so the logic here is if at our clock edge, if it's reset, I want to go back to an initial state. And then if it's not reset, I want to go to the next state. And it's as simple as that. Now, the actual logic of our finite state machine is going to come from how we determine next state. But the actual just transitioning state to state, super simple. If it's reset, go back to the beginning. If it's not, go on to the next state. So does that make sense what this block is doing and how it relates to a finite state machine? Okie dokie. Seems like it. So that is the second part of finite state machine. And now we're on to the actual complicated part. So the reason we learned our switch cases is because that's the best way to represent a state machine, right? If I'll have a state variable, and then depending on its condition, I want to execute different code. So we're going to be using a switch case where the different values of our state variable will determine different things. So I guess we can go back to SystemVerilog. I don't even know. I went back to the slides. So the idea behind this is we're going to be checking if any of our inputs come in and change. Depending on what state we're in, will determine what our next state's going to be. So the keyword that we just used there is that if any input changes, which means we learned an always block for this earlier. So if we put everything between an always column block, if any of the variables inside this block change, which will be our input variables, then it will calculate what state, based on what state we're in, it will calculate what state we need to go to. And to do that logic, like I just mentioned, we'll be using our switch case. So we'll have our case, and we're determining what code we're going to execute based on our state variable. And in fact, the state we're currently in, so our present state. And so this is the syntax for our switch case. And then we'll just have different conditions. So the condition we first want to check for is if we're in our sense zero state. What do we want to happen? So the first condition is if our present state variable is equal to sense_0, then we want to execute the code in here. And so let's actually go ahead and look back at our state diagram. So from our sense0 state, that's this first one up here, if we have a nickel come in, we want to go to sense 5. If we have a dime come in, we want to go to sense 10. And then if reset comes in, we want to go back to sense 0, or if no other inputs come in, we just want to be in that same state, right? So let's go ahead and implement that in SystemVerilog. So if nickel was high, so if nickel is equal to 1, then we want our next state to be sense 5. And then so really quick, just to sanity check what we're doing. So if nickel changes value, goes from 0 to 1, it'll execute this. And if we're in the sense 0 state, it will tell us our next state is going to be sense 5. And then at the next clock cycle, we just set the value for next state. So the next clock cycle, it'll come over here and be like, okay, well, present state gets next state. So next state down here was set as sense 5. So now present state will be sense 5. And we've successfully transitioned from sense 0 to sense 5 at the input of a nickel. And so the logic for this is going to be very, very similar for all of our different cases. So now we have else if our dime was high, and we want our next state to be sense 10. And then finally, if none of them were high, so neither nickel was high or dime was high, then we just want to stay in that same state. And so we want our next state, because remember, with this logic here, every single clock cycle, present state will change to whatever next state has been assigned. So if we don't assign next state to sense 0 here, this might change to something we don't really want. So we have to make sure, even if nothing happened, you would expect it to stay where it is. We have to make sure it's doing that. So we'll get next state, and we'll stay in sense 0. Where was I at? Oh yeah. At the beginning here, one thing I want to iterate or say though is it's possible that our always block, our always column, will execute more than once every clock cycle. Technically, it shouldn't ever happen based on how we design the circuit, whether or not our nickels or dimes are like one clock input and how long they last, and if they can ever be high at the same time. But just in case, just to cover that something wonky goes on, we want to make sure that our next state is always going to be assigned at the beginning so that we're not starting at like some weird value and who knows what's going on. So we'll set next state equal to 0 just at the top to make sure we don't have any of those overlaps. And similarly, with that same idea, we'll set our output as 0 just in case something funky is going on. It'll always reset at the start of this. And we'll see what's happening. And one thing I forgot to mention in this sense zero state, if we go back to our state diagram, is that it has an output of 0. So in our state, it actually, in fact, the way we have our state drawn, it's a more representation of this state diagram, which means that every output has an assigned, or every state has an assigned output. So regardless of what my inputs are at the sense 0 state, I want it to output 0. So we can do that outside of this if and else if stuff. We can just assign out to 0. And then it doesn't matter what the inputs are, the output will always be 0. So that's the basic logic behind a finite state machine. And now we just have to implement all our different states. So they're all going to be very similar. So I'm just going to go ahead and copy and paste. We got to change our values. So we'll have sense 0, sense 5, sense 10, and sense 15. And remember, with the syntax of these switch cases, we always want to default to. And this default, for us, it makes sense to just reset. So whatever our reset signal is what this should do. So we want our next state to be sense 0. We want our output to be 0. So it's just basically what our reset signal would do. And hopefully we never get to this default state, but we just need to include it anyways, or else we end up with latches. Okay, so now to the logic of sense 5, if we go back to our state diagram. So in sense 5, an input of a dime takes us to sense 15, an input of a nickel takes to sense 10, and then the reset signal is handled by that always block we did before. So this should be pretty easy. So if n equals 1, we want to go to sense 10. And then if d is equal to 1, we want to go to sense 15. And then if nothing comes in, we want to just stay in the same state. And then it's pretty much copy and paste for all the rest of these states. So we're at sense 10. If a nickel comes in, we want to go to sense 15. If a dime comes in, we also want to come to sense 15. I know it's dumb programming and you would maybe want to reset or refund a nickel or anything, but that makes our state machine way more complicated, so we're not going to worry about it. And then if nothing comes in, we just want to stay in the same state. And then all of these all have output 0. And in fact, the only one that will have an output of 1 is sense 15. And for sense 15, the way we have it drawn is actually we don't care about any of the inputs. It doesn't matter what comes in when we're in sense 15. It'll only be 1 clock cycle long, and we just want to go back to the beginning. So that represents the entire state machine we just drew. We have our 4 different states as cases for our switch case. And then in each case, we have the code that we want to execute if we're in that state. And that is the entire idea behind a finite state machine. Obviously, when you have more inputs and things get more complicated, you'll have more states and more conditions in your states and a lot more nested stuff going on. But since we have a pretty basic state machine going on here, it's pretty simple. Each state does basically the same thing. So does that make sense how we took all of our different components? So we have our different parameters to make our programming nice. Obviously, we need our variables to represent our states. We have an always block that drives the transition of states. So whether it's a reset or whether we just want to go to the next state. One thing I want to add here, we added it in our default case, but I forgot to do it here, is that if we're resetting, I don't care what the present state is or anything. I just want to go back to 0, and I want the output to be 0 as well. And then, so if it's not reset, we're just going to the next state every time. And then this always COM block down here with the switch case of our states determines based on what state and what inputs we have, what's our next state going to be for the next clock cycle. So are there any questions on how we did all this? Again, feel free to unmute or talk in chat. Okie dokie. So that is the SystemVerilog code for our vending machine. But there's a bit more we need to do. So after we've created the finite state machine, now we need to do the other part of SystemVerilog. So we've described the hardware in that module. Now we need to describe the simulation. So that's another file that we're going to need to make. So it will be another SystemVerilog file. And we will name this one, it'll be our test bench is what these are called in SystemVerilog. So the way I've seen the naming convention is just make sure that it's the test bench for whatever module you're trying to test. So since we're testing vending machine, we'll do vending machine and then some way to denote its test bench. So I would just do TB to just represent test bench. You could write out test bench, you could write test, whatever you want to do. But it'll be another module. And in that module, there's a couple things we need to cover. So the first one, at the very top of this, you always want to specify the time scale. So these test benches, what they're actually doing is basically advancing time as a simulation and then changing the signals at different times to represent waveforms. And so in order to advance time, we have to know what kind of time we're talking about. So how we do that is this time scale up here. So the first value is basically the scale of your time. So the way to advance time is this little pound and then a number. So the pound represents basically wait this amount of time. And then the number after it is that number times your scale. So for example, if we're talking a clock or we're running everything on a nanosecond scale, which we specify by 1 ns up top, pound 20 would wait 20 nanoseconds before executing the next line. The second value is the time precision. And for the most part, it's not all that important. It basically just deals with how rounding of weights is. So in our case, we're not going to be doing any like weight 10.5 nanoseconds is when the rounding would come in. So it's not very important. I have included a resource at the end to go over it if you're curious, but for today, we'll just be using timescale 1ns, 1ns, and we won't have to worry about those intermediate times. So at the very top of your test bench, you'll do, what is that, a tilde, I think? It's the one next to the one that's not a quote, you know, time scale, and then what you want to specify. So ours would be 1ns, 1ns. In this test bench, the whole reason we're making this test bench is we're testing that module we just created. So in order to do that, we have to instantiate an instance of that module. So very familiar or very similar to other programming languages where you're instantiating instances of classes. In this case, we're going to instantiate an instance of our module. So in SystemVerilog, we will have the name of our module that specifies basically what kind it is. So similar to when we did like logic 3.0 and it said, oh, it's some kind of variable. In this case, we're creating a vending machine. So it's of type vending machine. And then whatever you want to call it. So we'll call it test because we're testing it. And then we have to put in our inputs. And in fact, these inputs actually have to be specified before. So the inputs to our vending machine we created, we have the inputs N, D, reset, clock, and out. So we need to create those variables here. So I'm just going to make them all logic and let it figure it out. But we'll have logic N, D, and reset, and clock. And actually, I mean, I'm pretty sure we could do, I think they'll all be wires, but just to have them separate. So these are our inputs, and then we'll have an output as well. And so these are actual basically like variables specific to this test bench that we're going to add. These are the actual values we're going to be changing in our test bench to simulate changing values, changing the input values to our vending machine, which means we need to pass these variables that are specific to our test bench and will be changing as the inputs and outputs to the module we created. So the order we have it written, it's N, D, reset, clock. So we'll pass it in as N, D, reset, clock. And then we have the last one is out. So similar to other programming languages, it's dependent on the order you put them in. There is also a way to do it independent of order using like dot notation. So you would do dot and then the name of the variable in your module. So in this case, if we're trying to pass as the N input from our module, it'll be dot N and then whatever variable we're passing in. So in this case, we named it N, so it kind of looks dumb. So it'd be dot N and then of N. But that's a little bit confusing. So we'll just stick with the order today. So what we've done so far is created all the variables we need to drive our module, and then we've also instantiated our module. So now from here, we're basically just going to be changing the different values to simulate essentially a truth table for our vending machine. And we'll simulate it and see what the output looks like, and then that will be the whole thing. But really quick, we have one more thing we need to do, and that we need to actually create an alternating clock signal. Is that a capital C? Doesn't look like it. So there's a couple different ways you can do this in Verilog. So we can do the most simple way is, since we want this clock signal to always be alternating, we'll just have an always block with no sensitivity. So if we just do always, it will literally just constantly run. What's the hard way? I'll show you after. It'll literally run anything in here, right? It'll just continuously run it. So if we just make clock alternate, so we just assign clock to not clock. So if clock was 0, it would get 1. And if it was 1, it would get 0, which is how our clock works. That would constantly assign the alternating value. And then you have to specify, if we leave it like this, it will literally constantly alternate. I don't even know how fast. I think probably once every nanosecond, just because of how we specified our time. I mean, you could do that, but let's go ahead and make it a 20 nanosecond clock. So the way to do that would be, in that always block, wait 10 seconds or 10 nanoseconds, and then assign the opposite value. And then it'll run again, and it'll wait another 10 seconds and assign the opposite value. So essentially, you'll get a high pulse for 10 seconds, and then a low pulse for 10 seconds, and so on forever. Which is the whole purpose of a clock, right? So this is the easy way. Okay, let me think about the hard way. There's like, I mean, none of them are too hard, right? I mean, you can do this in exactly one line. You could probably do like an if else. Always begin if clock equals 0. And then assign it to 1, and then if clock equals 1, assign it to 0, and so on. There's different things. You can also do an assign clock to like not clock every 10 seconds or something. I think this does the same thing. There's a bunch of different ways. None of them are that hard, because it would be kind of a stupid language if we're working with like digital stuff, which all works with clocks, and then it's really hard to make a clock. That wouldn't make any sense at all. So for the most part, they're all pretty easy. I hope that answered the hard way, though. Okay, so we've done almost everything we need to do. Now we need to actually just drive the signals. So we set up our time, we've instantiated our module, we've created a clock, and now we need to actually just send in the different signals. So there's one more kind of thing we're going to learn in SystemVerilog, and it's an initial block. In an initial block, these are specific to test benches. They're non-synthesizable, which is where the simulation stuff comes from. It's not actually going to be hardware. It's just us telling the computer to do certain things. But an initial block runs everything inside of it once, just once. And so we'll use this to change all of our signals as if it were a truth table, just once. So the first thing we need to do is instantiate all our variables. So let's make n equal to 0. Let's make d equal to 0. Make reset equal to 0. And let's make clock equal to 0. And if we didn't set clock initially, I think that might be in capital C. Yeah. If we didn't set clock initially, it wouldn't really do this. Or no, the other hard way was always at and then a clock. And then if you didn't set it, it wouldn't do this. But because we didn't always block, it will always do this no matter the value of clock. It would just get really confused if clock wasn't set. It'd be like, what's the opposite of nothing? But just to be safe, we'll set all of our initial values. And then let's go ahead at the very start. Let's just reset the machine, because I don't know what's happening at the very beginning. So let's wait. We'll wait 10 nanoseconds so that all those initial values get made. And then let's go ahead and reset the machine. So we'll set reset high, and then it'll reset back to exactly what we want. And we will keep that high for 20 nanoseconds. And then we can begin actually changing our values. So now we know it's at our default state. So let's go ahead and set in n equals 1 for 1 clock cycle. So by doing n equals 1 and then waiting 20 nanoseconds, it will make sure that n is high for 1 cycle. And then we will set it equal to 0. And then let's wait another 20 nanoseconds just to see what's going on there. And so basically, we're just going to be filling out a truth table with different values here. So let's do the first one is where we just set n equal to 1 for 3 clock cycles, right? So we'll do n equals 1. So waiting 20 is 1 clock cycle. Waiting another 20 is 2 clock cycles. Waiting another 20, oops, sorry, n equals 1. and waiting another 20 would be 3 clock cycles. So according to us humans, if we set this for 3 clock cycles, that's us inputting a nickel 3 times, 15 cents. So it should give us our output of 1. So that would be one condition of our truth table. And now we just need to basically do them all again. But remember, after every single time we iterate through, we want to reset the machine, because ideally this is going to give us, once we get to 15, it'll reset and everything will be fine. But we don't want to just hope on chance. Let's make sure that it's resetting for sure. And we'll hold that for 20 nanoseconds. And we'll set it back to 0 for 20 nanoseconds, just to make sure it did reset. And then we can test another truth table thing. So I'm just going to go ahead and basically copy and paste this code over and over again and change our different values. So we should specify in each one here, because we have our 2 inputs, we should specify that d equals 0. Oops, I missed some semicolons. I'm sure I'm going to get some compilation errors, because there's no way I programmed this whole thing perfectly, right? We'll just go ahead and copy over all these conditions and do it for a couple different cases. So let's say we do a nickel 3 times, and then this one, let's say we do a nickel and then a dime. So remember, that should also give us 15. And then let's do, say, a dime, then a nickel. Or let's do a dime and then a dime, how about? And then that'll be our 3 conditions for testing. If it looks like it's good from those, it's probably going to work. So each one of these, here, let's go ahead and comment. So this would be, here we're doing our global reset. Oops. So that would reset everything. And then this would be the 3 nickel entry. This would be nickel plus dime. And then this would be our dime plus dime. And these just represent, basically, we're testing the truth table of our vending machine to verify it. Okay, so now we've created our module and our test bench. Really quick before we move away from the test bench, does it make sense how we created an instance of our module, created a clock, and then how we basically drove time forward to simulate sending in a truth table of values to eventually we're going to test how our response looks. That's what we're going for. But does it make sense how we've created it so far? Okie dokie. Sounds like there aren't any questions. So let's go ahead and actually try and compile and see what's working. So the way to compile a design is you could come up here and press compile, and it will do all of these. So it will synthesize and analyze your circuit, and then it'll like try and fit it to your device. Oh, the vending machine makes sense. Nice. And then it will, I don't even know what assembler does. That's probably like generate programming. I don't know. And then it'll analyze like the timing of your device and everything. And it takes quite a while if you compile all those things. Since we're not actually looking to really care about what this looks like on the device, we really only want to know if this, the code we have will actually synthesize and be represented digitally as hardware. So the way to do that is we can just double click on just analysis and synthesis, and it will only synthesize and then analyze that synthesis, as opposed to trying to fit it and place it and timing and everything. All right, we got 5 errors, so I'm gonna have to go through and troubleshoot really quick. So we have at line 6, near text parenthesis, check for a fix. I don't really know what's going on with that one. Let's see. Maybe it's an earlier. Out is already declared in the present. Oh, it's at TB. Okay, so it's on our test bench at line 6. Vending machine test. Hold on, let's scroll down. You guys are gonna watch me live try and debug, which is never a good thing. Identifier out is already declared in the present scope. Isn't that fine? Okay, maybe it doesn't like that these are above that. Let's try it It's probably the same error, isn't it? No? Oh. Okay, let's go look at my example code because I don't want to spend forever debugging this. So I think it's this one. Nope, that wasn't it. Let's open. Okay, I have two folders of demo. Ah, I forgot to declare module first, it looks like. Okay, so we got to do that first, apparently. Just copy and paste that line. Couldn't tell you. I guess maybe that's kind of like the include statement from other libraries. All right, let's try it. It's taking longer this time. Maybe that's a good sign. Dang it. Okay, this one is, looks like semicolons we missed somewhere. So line 11. Always begin. Oh, I forgot a semicolon there. And then line 83. I forgot. I don't even know. I don't think I lost any semicolons there. This is really fun, by the way, guys. It's not nerve-wracking at all trying to live program. I think the logic declaration's got to be back on top. We shall see. All right, one error. We are down to one. That is great news. Near text end, expecting semicolon. All right, let's see. Do I have to have like an end module here? Oh, you know what? We gotta finish. I forgot this is one thing I did forget for sure. This is a SystemVerilog command, $finish. It's just built into the language. And what it does is it tells the simulation software it's done. So that if you don't do that, it will just continuously run forever. And nothing will be changing except the clock every time. Does every wait need a semicolon, like pound 20 semicolon? Dude, that honestly very well could be it. Okay, expecting end module. Oh, yeah, I forgot that. We need an end module. Because you know what I forgot to do? I totally messed up the very beginning, is that we're declaring another module, vending machine underscore test bench. So even though this module we're creating is a test bench and we're not expecting to actually synthesize it, we still have to follow the same syntax of SystemVerilog in that first line needs to be, well, the first line can be timescale. You could specify that anyway. And then the first line needs to be the module we're creating, which needs to match the name of the file. And then at the very end, we need an end module. All right, fingers crossed this one's going to work. I feel like we're going to run into more errors. This is the problem with not, oh man. Okay, maybe they're in the other file this time. Okay, they're in the other file this time. Object next is not declared. Did I accidentally like mess up? Okay, line 41. Oh, yep, I put next. I wonder if I did that in it. Yep, every single state has that. All right, fingers crossed. Let's try it again. So this is why you want to do analysis and synthesis, clicking just directly on that, as opposed to the big compile button that stares you in your face, because it takes like 5 times longer and you're just fixing silly errors. For net out at vending machine. Okay, so this one actually might be a conceptual error, which is scarier to debug. So at line 32, I'm wondering if it's complaining because we have out being assigned every single time. You know how we can fix that? We can get rid of our outs everywhere. Now no state has an output. And then we will do, this is called a continuous assign. And we're going to assign out to only if our present state is sense_15. So if our present state is sense15, output will be equal to 1. If it's not, output will always be equal to 0. So let's see if that fixes it. And if it doesn't, I'm literally just going to go compile my other code that I wrote yesterday when I was preparing to live program this. And I was like, this is going to be miserable. It's the exact same code here. Procedural continuous assignment to register is not supported. Okay, well, I guess it didn't like that assign. So we are going to close that guy and move to literally, it's going to be the exact same code without whatever error I accidentally programmed in. So let's go ahead and do that. It's on my desktop. And then what date were these made? 12/1. Or I think this is, we'll go with this one. Sorry, I think I need to open a project. It's this one, I think. All right. Yep, this is literally the exact same code as we had. It's just probably what I messed up was these blocking versus non-blocking, which by the way, is probably one of the most confusing parts of SystemVerilog. You're going to get so many errors if you go into this language with stuff like that. So let's hope this analyzes and synthesizes so I can show you guys how to actually simulate. Otherwise, we're running out of time. Okay, this one compiled, which is great news for us. So once we have it actually synthesized, so now the software knows like what the physical circuit's going to look like. Now we go to tools and we're going to simulate that circuit. So it doesn't matter which one of these you choose. It's basically just a different level of abstraction, whether you're looking at like physical gates versus the concept of a D flip-flop as opposed to the gates of a D flip-flop. So it doesn't matter which one you really do for us. So now this opens up the Model Sim Altera software that you guys, if you follow the installation, we'll also have this, and we set it in our project settings that we simulate with this software. It's not a good software, by the way. Would not recommend this. It's such a clunky user experience. But to actually simulate our thing, we're going to go to compile, and then we are going to compile together our module that we're trying to test with the test bench we're trying to use to test. So we're going to compile those two. And if you get any errors here, good luck. Compiling is, I will never be able to give you a one-stop answer. You're probably gonna have to Google stuff. But luckily ours compiled. So then we're gonna go and on the module that is the test bench module, which we'll have to hover over. Okay, so this one is vending machine .sv, which you can see at the very bottom when I hover over it, as opposed to this one is the test bench. So we're gonna double click on our test bench and it will open a new window. And then from this window, we're going to, so all of our different variables we had in there, we're going to add them all to a wave because how we're going to analyze everything in SystemVerilog. Well, there's more complicated, like you can like do like test print statements and stuff that print if something goes wrong. But today we're just going to be looking at the most basic, which is analyzing the actual waveform and pulses and stuff. So we're going to add all of our variables to the wave. And that will open up another window. And this is what I mean by the user experience is horrible, because then it closes that window and you have to go reopen that window. And then up here is how you advance time in the simulation. So you can run it for 100 nanoseconds by clicking this button. You can run it, I don't even know what continue run does. And you can also run all, which this will just run your entire program. And if there is a finish that you added at the end, like we did, it will run to that point. So since we added a finish, it will say, are you sure you want to finish? And this is what I mean by the user experience. It's horrible. If you click yes, this whole window closes and everything we did just did nothing. So you have to click no and then go back into that window. And now you will see a waveform. So on the left is all the different variables of our test bench that we created. So we have our 3 inputs, ND, reset, I guess 4 inputs, we have clock too. And then our 1 output, out. And the way to analyze a waveform in SystemVerilog is to literally progress along it. Pretty much you want to do the pause edge of these. So there's these buttons up here that let you find like transitions. So I want to find the next transition that is a positive edge. So it'll advance. Okay. I don't know if that's the right transition. I think one of these is rising edge. Oh, that's previous rising edge. So now we want next rising edge. Oh, it's because I'm selected on the reset variable. That's why it's advancing so much. So if I select the clock variable, I can move along each rising edge of the clock, which is, remember, how our code was executing. So if we look at it here, at each clock edge, it checks its state. So this is after all the resets and everything have gone through. And so now we have our first input. So this first input of n gets recognized. And because our present state up to this point was 0, you can actually go ahead and include the present state variable. I think I got to go back here to the module that we were testing. So let's go ahead and include the present state and next state variables by selecting them and also adding them to the wave. I think I might have to restart. Yeah, we gotta close this and resimulate. Okay, so add to wave. And then we're going to go back to the actual module we were working with. It has its local variables, so present state and next state. And then we're going to add those to the wave as well. So now in our wave, we should have all 7 of our variables. Let's make sure we can expand so we see all the names. And it looks like we've got to resimulate. Okay, I think that we want to reset. Let's look for a reset button. Restart. And then run all, and we don't want to finish. Okay, so now we can analyze this. So we were right here at the first nickel input. So this nickel input goes high, and the present state was 0 cents, because we have our present state variable was 0001, which remember was cents 0 as the variable we set. So as soon as that nickel went high, it registered and moved on to the present state of, or the next state immediately changed to 5 cents. And then at the next clock cycle, which is this positive edge, our present state becomes that 5 cents. And then moving on to the next one, we have our dime here. So we're in our present state of 5 cents. Our dime gets registered. And so it says the next state should be 15 cents. And so the next clock cycle, it will go. And you'll notice our present state now becomes 15 cents. And our output becomes 1. And then you would analyze that over and over again for your truth table. It gets pretty tedious. Which when you get better at SystemVerilog, there's different ways to verify like where signals are high and where they're low and stuff like that. But the actual, like, if you're ever confused, you literally come in here and check rising edges and falling edges and what the variables are, when and where and why, to check the behavior of your vending machine. So ours, I could tell you I verified it yesterday because I took the time to program this, even though it doesn't look like I did. And it does work out that it follows the logic of our vending machine state diagram, which makes sense because that's what we programmed it off of. So that is how you would create a vending machine based off of a finite state machine. And then how you would create the test bench, I don't have it open, that lets you test the truth table for this vending machine. And then combined, putting it all together, you would compile it and simulate it and analyze your waveform. And if it's good, you're done. If it's not good, you got a lot of debugging to do. Takes a long time, believe me. But yeah, that is an introduction to SystemVerilog. So today we covered different variable types, the idea of always blocks and how and when to use them. We covered some control statements like if and else, and also some switch cases. With all of those combined, you should be able in SystemVerilog to recreate any kind of finite state machine you want, because the idea is always the same. It just gets a little more complex with a bit more variables and stuff and more states. But with that foundation, you could do anything finite state machine related. And then you could also create test benches and simulate and read the waveforms as you need. So it's 4:30. I want to take this time to advertise that we will be continuing this workshop series, mainly because I am a SystemVerilog lover. I can't say that. I'm a digital design lover. SystemVerilog is one of the better ways to do that. So next quarter, we will be having a part 2 to this workshop where we will be covering, I haven't decided exactly what communication protocol we're going to be creating, but we will be creating some kind of communication protocol in SystemVerilog, whether it's I2C, UART, SPI, or something like that. I believe the tentative date on that one is like February 7th. So if you guys are interested, it's not posted as a Facebook event yet. It will be coming out sometime in winter quarter because I didn't want to worry about it on finals week. But keep your eyes posted. It's sometime mid-quarter, next quarter. And if you're interested and you enjoyed this SystemVerilog, I'd love to see you guys out again. All right, so we got a couple questions in here. So where will this recording be posted? I believe we have an IEEE UCSD like YouTube. So this recording will get, I'll send the link to somebody tonight, and I believe they upload it to YouTube after. And then how can you be notified of the next workshop? My best advice for you guys if you want to keep up with IEEE workshops is to follow the IEEE Facebook page. Every event, whether it's social, professional, or technical, will get a posting of what the event is, where it is, how you can find it, and then if you need to install anything or anything like that. So that would be your best resource. Also, I believe we have a newsletter and a website, but I don't believe the website gets like currently updated with events. So best bet would be Facebook page. But yeah, that's SystemVerilog. I'll stick around if anybody has any questions on the language or anything. But otherwise, I hope to see everybody at the next part 2 of this. Thanks for coming out.
I have a question. It's not about the language really, but I was just wondering, so I'm obviously an ACD major, and I'm interested in like hardware and stuff and digital design. And I was wondering if you've used Verilog in any of your internships and like how you use it, I guess.
So I am a 3rd year. I've only had the opportunity to have one internship. I'm in the process of applying for a bunch of them right now. And I worked as a systems engineer. So I didn't actually directly do any like digital design or anything. So unfortunately, I did not use any like Verilog or SystemVerilog in it. I know I have one friend who said he did a digital design class or a digital design internship, like that was his title. So I can give you his email. I doubt, I haven't asked him of this, but I'm sure he'd be more than willing to help if you have any questions. Does that suffice?
Yeah.
All right.
Yeah.
I guess I should probably stop sharing my screen because it's technically my DMs, but that's literally all just class related.
Are you thinking of going into digital design as a career, or is it just like something that you enjoy learning about?
It's kind of the whole reason I got into electrical engineering is I was really curious how to like take binary stuff and like convert it to a computer basically. So it's what I like about electrical engineering. I do plan to try and intern in it this year and see how I like it as a career.
Yeah, well, good luck. I hope you get it.
Thank you. You as well. What year are you?
I'm a 1st year.
I would recommend, I mean, there's no reason not to apply to internships. They might still take you, but yeah, I wouldn't worry about it too much in freshman year.
Yeah, gotcha. All right, are you gonna DM me his email or should I stay in here? Are you gonna put in the chat?
I will, can you send your email in the chat here?
Oh, yes,
Or actually, what you could do is just, the best way would probably be to shoot me an email so that I have your email, and then I will like CC Mahmood if he says he's willing. So my email is Sebastian. And if you just shoot me an email like digital design question and something, I will.
It's a cool email, like Sebastian, but Sebastian.
You know, I haven't actually considered that. I didn't.
That's pretty cool. Nice. Okay, I'll send you an email. Thank you. Okay, have a good day.
Yeah.